Welcome to this very first episode of FireDevlog. This is going to be a more informal series where I want to share some ideas and updates and also behind the scenes thoughts about things that I'm working on. I consider this to be a bit of an experiment and we will see how it will turn out. For this first episode I would like to introduce FireSciPy. This is an open source Python package that we have been working on for some time. The long-term goal of FireSciPy is to include a wide range of models and correlations used in fire safety engineering, such as design fire generators, plume formulas, or ceiling jet correlations and the like. But it doesn't stop there. FireSciPy is also meant to provide data analysis tools. For example, methods to determine kinetic parameters of pyrolysis reactions. This is further bolstered by modules for pyrolysis modeling itself. The initial focus of this package is on pyrolysis, starting with an isoconversional method to determine the activation energy. It also provides some basic functionality for simulating pyrolysis reaction rates. If you are familiar with the Python ecosystem, you may know that there is many packages that are providing very fundamental capabilities. NumPy, for example, would be a package for fundamental computations, for example matrix computations and things like that. But it is fairly baseline in terms of its capabilities. Then there's packages like SciPy, which are built, for example, on NumPy, which provide more elaborate computational methods. These two packages are very widely used and they are also the foundation for this FireSciPy package. Right now FireSciPy does not contain much. For example, there's a very simple design fire generator within the hand calculation section. For this initial release, the focus is on kinetics computations for pyrolysis reactions. This is primarily motivated because these are things that we are working on right now. Recently I spent quite some time to set up the documentation for the package. It actually felt like it took way more time to write the documentation and all the tutorials and whatnot than actually writing the code itself. The GitHub pages are here used for the documentation, which is really neat because with the package swings, the doc strings from the functions can already be read out and automatically the API documentation can be generated. Like for example here in the pyrolysis section under modeling, there is a definition of the reaction rate function. Then I've provided here in the doc string information about what the function is supposed to do and also some mathematical equations. I've written the doc strings in the RST format, which is the restructured text. Swings can then transform the information from the RST format into nicely rendered formulas on the GitHub pages. So we see here again under FireSciPy, pyrolysis modeling, the function for reaction rate. There is the description of the doc string and nicely rendered formulas. I've also put in some effort to highlight from which specific literature source I have taken the formulas that are implemented here. There's also links to the articles provided so that it is easy to assess what the source is. These doc strings also contain the classic information about what are the parameters that are going into the function and then what the actual returns are. This is then here set up for all the public functions of the package. The documentation can nicely be reached from the main page of the Git repository. On the top right there's a link to the GitHub pages. For now the documentation is split into two chapters. The first chapter contains tutorials and the second chapter contains more targeted documentation. For example, if you click here on the pyrolysis module, you get the API documentation describing the functions, the doc strings of the functions and all the parameters that go in, the results that are produced, all these things. I've also set up a usage example. This right now only contains a simple design fire generator. For example, in this case, the idea is that the user knows a function design fires exists in FireSciPy, but maybe they can't quite recall which specific parameters are being used for what. And then here is a very bare bones example, which parameters you use, how to call the function, and then what you get as a result. I also spent some time to set up the tutorials. Specifically, my focus was on the pyrolysis reaction kinetics. As a start, there is an explanation how pyrolysis modeling can be done with FireSciPy. In the second step, an isoconversional method to determine the activation energy is discussed. Specifically, the Kissinger-Akira-Saunders method. This second step is built on the reaction rate modeling that is discussed in the first step. Basically, artificial data is generated to mimic TGA experiments, and then the procedure is demonstrated how the KAS method works. And in the third step, actual experimental data is provided so that you can get an understanding for how to use the package with proper experiment data. Let's have a brief look at one of these tutorials. These tutorials start out with some theoretical background at the top and also sources where you can read up on things. This is then followed by the actual Python code that you would need to use to run your assessment. For all these pyrolysis computations, I have been looking into the ICTAC Kinetics Committee recommendations. My intention here has been to implement an isoconversional method to deduce the activation energy from the thermogravimetric data. In the beginning, I wanted to implement the Vysovkin method because, according to these recommendations, this is one of the most accurate methods that you can have for this. So, but it turns out there is an optimization step which needs to have an initial guess value for the activation energy. To get this initial activation energy, I went a step back and implemented a more conventional method, the Kissinger-Akira-Sonos method, or KAS method. While implementing the KAS method, the question arose, how do we check if it is implemented properly? This is then what led me down to the path to implement some basic modeling capabilities. This then helps to figure out if the KAS method produces the same activation energy as the one that went into the model. There exists a bunch of other isoconversional methods that are similar to the KAS method but are less accurate. For example, a very well-known method is the Ozawa-Flint-Wall method, the OFW, but it is known to be inaccurate. The question for me is now, should I actually go into the effort to implement methods that we know are less accurate or not? So maybe if you have some thoughts on this, please provide some comments and some arguments why you think the other method should be implemented too. There's different places where you can provide the comments. For example, you can either directly comment under the video. You can also go to the Git repository and use the forums or the issue tracker. But we will then also have some discussion about if it actually makes sense to implement these methods. So please provide arguments, not just I want to have it, provide an argument for why you think it is actually necessary. Again, right now, for the initial release, the KAS method is the one that is implemented in FireSciPy. Next to these tutorials available on the GitHub pages, I've also created a Jupyter notebook that you can download and directly test out the things. This Jupyter notebook essentially contains the same tutorials that are provided on the web page. It's just nicely packaged into the notebook, so you can just run all the cells and have the output and can directly play with it. So as you see here, there's a single-step pyrolysis kinetics modeling, the theoretical background in the beginning, and then how it is done in Python. From the main page of the Git repository, you can find this notebook in the docs, tutorials, pyrolysis, and then there's a directory notebooks. And here you see the FireSciPy KAS demo notebook. You can nicely download this from here, and if you go one level up, where the notebooks directory is, there's also a data directory, and in this data directory you find the experimental data that is used for the notebook to show you how the real data analysis works. As for the next steps, right now I'm working on bringing this package to PyPI. With that, it will then be available to install via pip. I also intend to create tutorial videos. Depending on when you watch this video, they may have already been released. Once the initial version is available via pip, I will then work on implementing the Wirsovkin method. Other than that, thank you very much and have a nice day.